What up, mathletes? Whoop, whoop. All right, this is 4.1, our new module. Learning target is I will graph linear functions by using tables and intercepts. Let's get into this. So write that down and then go ahead and work on the warm-up, which says just state the domain and range of each relation to determine whether the relation is a function. Oh, gotta stretch it out sometimes. All right, so pause this, give it a shot, ready, set, go. And now I'm going to do it for you. I'm just going to do it like I'm mapping every time. Which, by the way, you'll notice this is already done for you. Here's my domain. Here's my range. Here's my domain. Here's my range. Okay? So I'm going to do the same thing here, but don't forget we don't do repeats. So I've got 7, 4, 3, 2. No repeats there. Okay, and let's see, 2, 3, and then 2 4s. So we're just going to do that once. And let's go ahead. So this is my domain, this is my range. Let's determine if it's a function or a relation. So let's see, 7 goes to 2, 4 goes to 3, 3 goes to 4, and 2 goes to 4. Notice that each of the domains only go to one range. That's a function. So this is a function. Okay, let's go ahead and do this over here. Again, I'm going to do the same deal. So I've got 0.9, 1.4, 3.2. And over here, I've got 1.4, 0.8, and 1.4. Let's see how this works. So 0.9 goes to 1.4. 1.4 goes to 0.8. And, oh, I listed that twice. I didn't need to. And 3.2 goes to 1.4. Again, two buttons can give you Pepsi, right? But what we notice is each domain only goes to one range. So that works perfectly because this is my domain, this is my range, so this is a function. Let's look at this one. Again, looking just at the domain. Each domain goes to only one range, therefore this is a function. Oh, Texas can go to both Houston and Dallas, and Ohio can go to Cleveland or Columbus. These domains go to 2 ranges each. That's not good. That's like pushing a button and getting in either or. We don't want that. So this is a relation, not a function. That's the difference. If it's not a function, but it still has a relation to each other, it's just a relation. Okay, we're going to move on today. What I want to tell you, this is graphing linear functions by using tables. Every ordered pair that makes the equation true represents a point on its graph. A graph represents all the solutions to an equation. Okay? So let's look right here. And I want everybody to practice. You're going to make a table. It's called an XY table. And we're just going to go from -2 to 2. And here's how you would work it out. Before we even graph, well, we'll worry about that in a second. So what we're saying here is every ordered pair that makes the equation true represents a point on the graph. So we got to find points. So you start out with x, and we have our rule right here. 9x plus 3y equals -12. So we're going to take that, and I'm going to plug in -2. So I'm going to have, all right, so the first thing we got to do is solve for each. I'm going to solve this for y. The reason why I'm going to solve it for y is when I solve this equation for y, I put it in a form that I can just plug in an x and get out a y value that will help me. So I'm going to say, all right, 9x plus 3y equals -12. Okay, I'm going to subtract 9x from both sides. Now, I can't combine these terms, but watch this, 3y equals -9x minus 12. I'm always going to put the x term first. Last, I need to divide everything by 3. Divide by 3. Boom. What's negative 9 divided by, and I'm going to get y equals negative 9 divided by 3 is what? It is negative 3x. Negative 12 divided by 3 is minus 4. So now watch what I can do. I'm just going to plug in each of these values. I'm going to say, all right, so that's step 1, step 2, plug in x to get y. That's why x is independent. We can pick whatever x we want, but whatever x we plug in is going to get us a very specific dependent y. So I'm going to have y equals negative 3, and then always in parentheses, times negative 2 minus 4. Negative 3 times negative 2 is positive 6, minus 4 is 2. There we go, 2. Y equals negative 3. This time I'm plugging in negative 1 times negative 1 minus 4 equals 2. Or I'm sorry, it doesn't equal 2. Negative 3 times 1 is negative 1 is positive 3. Minus 4 is negative 1. I was just copying up there. So this is minus 1. So that becomes 3 minus 4 is negative 1. 0 is always our friend because we can say y equals negative 3 times 0 minus 4, and that just cancels out, so I get negative 4. Now at this point, you may be noticing a pattern up here. Is everybody noticing it from 2 to negative 1 is plus 3? From negative 1 to negative 4, I'm sorry, not plus 3, minus 3. From negative 1 to negative 4 is minus 3. I bet you I'm going to subtract 3 again. Negative 4 minus 3 is negative 7. Negative 7 minus 3 is negative 10. Let's see if that's true. Okay? So I'm going to have y equals negative 3. Let's try the first one times 1 minus 4. Negative 3 times 1 is negative 3. Negative 3 minus 4 is negative 7. Certainly looks to work. Let's try it again. Y equals negative 3 times 2 minus 4. It's going to be negative 6 minus 4 equals negative 10. Look at that. So I was able to use the pattern to predict future values. You can use that to help yourself fill out tables. Let's go to graphing. So when I go over here, okay, let's use this to predict graphing. So when I go over here, first of all, let's, I like to put in my arrows, go ahead and do that, and label this the x-axis and the y-axis. It's already labeled numbers for us. I don't like all the numbers, but they're already there, so we'll deal with it. And let's put in our points. Do you notice that if I were to put parentheses around these, that looks like a coordinate, negative 2, 2. So I'm going to go negative 2 on the x and up 2 on the y. And I have the point negative 1, negative 1. So I'm going to go negative 1 on the x, negative 1 on the y. And I'm going to now go to the point 0, negative 4. So 0 and then down negative 4. And 1, negative 7. So 1 and down to negative 7. And 2, negative 3. 2. No, excuse me, negative 10. 2, negative 10 right here. Boom. And you always want to get a straight edge. I'm going to use a ruler. Connect these dots all the way through. Notice that I can connect it with a straight line because this is linear. And that means that also shows us these points are accurate because I was able to connect them all with a single line. Now, when you draw a line like this, guys, I always want you to label it. So we're going to label it right here. I don't care if you use either the standard form. I'm going to go ahead and use what we solved it to be, which is y equals negative 3x minus 4. Then we know which line is what. And that's how you graph using a table. Now, using a table, you want to be smart in the values you pick. So I want to kind of go down here. Again, pause this as needed. I'm going to move on to the next. Look at the bottom of this page. So it has 3 minus 2/3 x. Guys, listen. Do I want to pick a bunch of values that are going to get me these weird answers. Can you think of graphing those on a small graph like this? No, that'd be a terrible idea. Okay? That'd be a terrible plan. And I'm certainly not going to put in weird values of x to make it work out, so this would be a terrible plan. What I want to do is I want to pick values of x that are going to get me good values of y. Notice that if I multiply anything that's a multiple of a 3, it'll cancel out this 3 right here. So if I use like -6, right? So y equals 3 minus 2/3 times -6. Now watch this. First things first. This is going to be 3 plus, because a negative times a negative is a positive. But then 3 goes into 3 once, goes into 6 twice. And I'm left with 2 times 2, which is 4. And that is 7. Ooh, by the way, this brings up something else. When I plug in 6, it gets me 7. Over here, it got me -1, so now I know this table is wrong. But look at the other values they picked. All of these are multiples of 3 to make sure that when I multiply it out, I get a whole number. As you're choosing your table values, always choose values that'll get you a whole number. Don't just choose values that'll get you these random in between. That's terrible. It's a terrible plan. Okay?